Alrighty, we are up and running. Welcome back. We are now in the second part of lesson 8, I believe we are on. Excellent, we're almost there. One more lesson after this, and we are done. So this is the second part of the introduction to time series. So last time we talked about, well, what is a time series, how we can decompose a time series into its different components. Now what we're going to talk about is the second part of this, which is the forecasting. So imagine it is October and you need to decide how much holiday inventory to order. Order too little and you lose sales. Order too much and you incur storage and markdown costs. Now, balancing supply with uncertain demand is the heart of forecasting. So this is, we can kind of think of this as the kind of the classic trade-off in retail. If we underestimate, we miss out on revenue. If we overestimate, we tie up capital in unsold stock or pay markdowns to be able to move things if there's an expiration date on something. So forecasting gives us a data-driven way to navigate that sort of tension. So we're going to start with some basic baseline tools. The first is the naive way of being able to do this, and then smooth the noise using moving averages, and then add responsiveness with exponential smoothing, and then finally get into trend and seasonality with the Holt-Winters method of being able to do this. So a lot of little things to cover in this. All right. So the primary application of time series analysis is that of forecasting. So this is the key part here. If evidence exists that previous patterns in the data set will continue into the future. So if we believe that what we have is going to repeat itself or it's going to continue on in the same way. So if trends are going up, if trends are going down, and we think it's going to continue, then we do have various techniques that can be used to make forecasts. So to give a better educated guess than just something randomly or just some random guess overall. So again, as I said, the forecasting tools that we're going to be talking about, the baseline is the naive forecasting. Then we're going to try and smooth out some of the data. So we're going to do a moving average, and we're going to talk about exponential smoothing. So exponential smoothing is an idea where we're going to take more recent information and apply that. And then we're going to add trend and seasonality using the Holt-Winters. All right. So as I said, a fair amount of things to cover here. All right, so we'll start with the naive forecasting. So before we reach for moving averages or exponential smoothing, we can ask the question, can I beat simply forecasting that the next month will be exactly like this month? So if not, the question is, well, why complicate things? If we can't do better, or there's no reason for us to think we can do better, then let's just match what we did beforehand. Now, the key points here is there is no assumptions that need to be made. You don't need stationarity in any model to be able to do this. And this is kind of like a benchmarking role. So if your fancy model can't beat the naive forecasting in accuracy, you're likely overfit or misspecified the data that you have. So many forecasting say competitions and business teams start by measuring performance against this naive sort of rule. So sometimes the simplest forecast is surprisingly, again, hard to beat. So we're simply just saying, if I'm trying to estimate at time t plus 1, I'm just going to use whatever it was at time t. So that's it, that's all. So I go one step into the, whoops, let's go back here. That shouldn't have gone ahead. Pen. If I go one step into the future, how do I calculate that or how do I predict that? I'm just saying, well, what was it at time beforehand? So my next period is going to be exactly the same as this period. All right, so why use this? Again, it serves as a benchmark for all other methods. If we're not beating this, then why are we trying to make this more complicated? And again, requires no parameters or tuning. So we'll talk about that when we get to the Holt-Winters method where, we have to specify specific parameters, and well, actually even in the exponential smoothing, we have specific parameters that, we want to be able to try and optimize to give us the best possible result. So if last month sold 1,200 units, using this method, we plan to sell 1,200 units next month. And we do this until you can prove that you can do better. Do I have anything? No, I didn't put an example on in there because that's fairly straightforward. But again, we'll use that as the benchmark, so it's good to include that in there. Okay, but let's say we can do a little bit better. So one of the things that we're going to try and do is just simply smooth out the data. And based upon that smoothing, we're going to predict from there. So it's very, very similar to that centered moving average smoother that we had before, except it's going to be a slight twist. It's not going to be a centered anymore. All right, so instead of a centered moving average discussed previously, we will use a predictive moving average for forecasting future values. So we're getting rid of the whole idea of it being centered. And remember, the idea of it being centered, if I was to replace x sub t with s sub t, my smooth data, what I do is I start at position x sub t and I go equal amounts to the left, equal amounts to the right. I take the average of those values that I have, and that's exactly what I'm doing for my smoothing. So here, again, it's not centered anymore, and I'll show you in a second what exactly I mean by that. All right, so if the data does not exhibit seasonality or trend, so this is not going to take into account seasonality or trend, we have other models for that. Then to predict the values of the time series at time t plus 1, it makes sense to predict xt plus 1 to be the average of the previous k data values, again, for some order k. So we say, let's let xt plus 1 denote one step ahead prediction. So if we know what time t is, t plus 1 is going to be one step ahead. And what we're trying to predict is just this xt plus 1. So the hat or the squiggle on top of that just means we're doing a prediction. So if I want to do one step ahead, this t plus 1, what am I doing now? Again, this is where we kind of get away from that centered. So now I'm trying to predict t minus 1. So what am I going to do? I'm going to start at time t, the one just before that. And then I'm going to go the one right before that, all the way up to k points before that. So I'm going to t minus k plus 1. So I have k data points. So whatever I'm trying to predict, I take the previous k points and I divide it by k. That gives me my average. Now, we don't have to create a function that does it. It's already built in for us. We just have to use the ma.pred.wge function, which we'll show an example of that in just a second. But that's all we need to do to be able to, again, predict into the future. Now, there is limitations to being able to, or limitations to using this, as we'll see when we kind of go through the example here. But again, it's one step above that, just saying it's exactly the same as what it was the time before. So you saying what it was the time before is just saying I'm taking the most recent bit of information and I'm just copying exactly that. Here what we're doing is we're going, well, I'm taking the last k months or the last k periods and I'm going to take the average of that, and hopefully based upon that average, all those fluctuations that would have happened in there, we smooth those out, and this is going to help me get my prediction to what it should be. All right, so for exercise 5, we're going to use the data set WT Crude 2020, which shows monthly prices of West Texas intermediate crude oil for the years 2018 to 2020. Actually, there's more than that, but we're going to focus on those specific years. So we're going to use the function ma.pred.wge to calculate one step ahead predictions. So if I'm trying to predict at time t, or if I have up to time t, I'm trying to predict one step into the future, so that's t plus 1. And we're going to do a fifth order smoothing. Now, much easier at this point in time to do these predictive smoothers, because again, I don't have to worry about whether or not we're even or odd, as we did in the center, because with the center, when it was odd, I'm going equal amounts to the left and equal amounts to the right. I'm still doing the same thing when it's even, except I'm taking a half to the left, I'm taking a half to the right, and then kind of averaging those out as well. All right, so let's jump into R. Might have to, because I restarted some of this, let's just recall some of these libraries here. So there we go. Where's my exercise 5? All right, so the first thing that I'm going to do is I'm going to bring in the data set. Now, I think I might have done this for an exercise 4. I can't remember. That would have been from the... Oh no, we didn't do this. Sorry, I did actually have something like this. So let's actually take a step back here. And again, if I was editing this, this would be so much better. Let's do the naive approach here for a second. So the first thing I want to do is I want to bring in my data set. So I'm just going to use the data function, calling WT Crude 2020. And if I just call the data set here and print it to the screen, notice we have a large amount of years. Oops, let's go down here. So we have all the way up from 1990 to 2020. And this is going monthly, so it's from January all the way up to December. Now, when we started this, we said we just wanted from 2018 up to 2020. So I don't want all of this information. So let's cut a little bit of it down. Now, how do we do that with a time series? We're going to use the window function. So the window function can be used really in kind of three different ways. So I'm taking a subset of my time series, but it's in continuous chunks. So what I'm doing here is I'm calling the window function. The first input is my time series, so that's a WT Crude 2020. And now I'm putting a start point. So I'm saying start is going to happen in 2018 on the very first, in this case, day, or it's not day, well, because it's broken down into a frequency of 12, so this is all done in months, so that one represents the first month. So 2018, January is where we're going to start. Now I haven't specified an end date, so it's going to start there and it's going to go right to the end of the time series, so that's December of 2020. So that's one way of calling it. Another way of calling it is I can just say, instead of start, end. And I can say end at 2018-1. So it's going to go all the way up to, but not including January of 2018. So it's going to go all the way up to December of 2017. So it's going to start right at the very beginning from 1990 all the way up. So if I specify just end, it's going to take from the very beginning all the way up to that point. If I have a start date, it's going to take from that start all the way to the end of the time series. Now I can also do a start and end. Again, end has to come after start, obviously, for this to work out. But I could say, let's go from 2018-1 all the way up to 2019-1. So I'm grabbing just a year out of there. So I'm going to store this in WTC 36. So this is going to give me 36 months worth of data. And just using the naive function here, I'm going to call that time series that I just created, the WTC 36. And I'm setting H equal to 12. Well, let's actually just call this up for a second. Let's do question mark. So what does H represent in this case? So H represents the number of periods for forecasting. So let's suppose I'm going to go in this case a full year into the future. So I'm setting H equals to 12. So if I do this and we plot the data here, so what we have here is the ups and downs starting at 2018 in January all the way up to 2021. Well, it ends in December of 2020. And so we're predicting a year into the future. So we're going from 21 to 22. And notice it's just a straight line because that's all it is. It's just taking what was the last time period, which happens to be here, and it's going to continue that on. No change, no trend, no seasonality. It's just this. All right. Now let's go to the exercise 5, which is using the order 5 smoother. So I'm using the function ma.pred.wge. So we're starting on line 130 of the R file. The first input, again, is that time series, that WTC 36. The order, again, how many data points or how many previous data points am I grabbing? I'm grabbing 5 and taking the average out of there. The n dot ahead, that's similar to the h above here. So the n dot ahead is equal to 1. I'm going one step into the future. And I want to plot this. So I'm saying plot is equal to true. So I'm going to save this to MA5. And if I output MA5, so a couple of things to notice here. So my original data, I have 36 observations for the 36 months. Now, I have 37 observations in my predicted vector here, but notice the first 5 are NA. Well, I can't have observations in there because in order for me to predict into the future, I need at least 5 observations. So if I look at the first observation, so if I'm trying to predict x1, I need 5 previous, but that's my first observation. I can't predict that. So I have to go all the way up to observation 6 and take the 5 previous to be able to predict 6, and that's exactly what we have here. And I predicted observation 37, so this would be January of 2021. So the prediction of that, well, what was December? December of the year previous was 40.75391. Now, if this was the naive version of this, my next month would be 40.75391, but it's not because I've taken it order 5 smoother here. So my prediction is 42.02270. All right, so the question now becomes, how good is this in terms of prediction wise? Now notice in my graph that I have here, I have a lighter dark here, and then I have a much darker black here. So the much darker one, these are our predicted values. So notice that they start at time 6, whereas the other one starts right at the very beginning. And we have an increase, some fluctuations, a big decrease, an increase. But notice what's happening here. The reaction time is less. So as I have right here at this point in time, I see a steady drop for 2 periods and then an increase. Well, at this point in time, it's still seeing an increase, and then it sees a slow decrease over the next, what is this, 1, 2, 3, 4, 5 months, a slower decrease instead of a major decrease in 2, and then a start to increase from there. That's the smoother that's happening here. It's smoothing out those things. So it's not as responsive as we may want it to be. But again, in terms of those overall predictions, if there is a lot of fluctuation, this might be a very valid model for being able to do this. So now, well, what if I wanted, again, as I said, to understand how good this model is at being able to predict things? Well, one of the things I can do is I have 36 data points. My original 36 data points are my 3 years worth of information. Now I've just predicted 37 observations, but if I take those 36 observations, unfortunately the first 5 are just NAs, but if I looked at all of the other ones, I could say, well, what's the difference between this and the true value? Because I have the true value. So I can do those calculations here. I can take the original minus the predicted. So going from 1 to 36, I'm not predicting into the future because, again, that observation 37, I don't have a true value for this. So if I do this, I take the difference between the two, and I'm going to store this in ma5.error. Notice ma5.error, the first 5 observations are still NA because I subtracted NA from the real value. I want to sum all of these up, but I also want to square each one of them because I don't really care if it's negative or if it's positive. I just want to know, well, how far away were we from the true value? So I'm taking the sum of the squares of the errors. Now what I'm also including here is an na.rm equals to true, which means I'm looking at this vector and I want to remove anything that has an na. If I don't do this and it tries to square this and add them all up, it's going to throw you an error and it's not going to be able to do those calculations. So the sum of squares error that we have here is 3,261.382. Now, is that really helpful to us right now? It's not, but if I had other models to compare this to, then I would see the smaller the error, the better off I am. So it's at least a starting point at least that. All right. Let's jump back to my slides here. All right, so a couple of things to note. The first one, because the moving average predictor is a 5th order, the data begins at t is equal to 6. As we already said, the first 5 observations are NA. 2, the prediction at t is equal to 6 obtained using the first 5 data values is 6496, while the actual value at t is equal to 6 was 6752. So again, fairly close at that point in time. At time 12, the predicted price was $67.30, but the actual price was $48.64. Remember that massive drop, it didn't catch right away. So a drop in prices that was not anticipated by moving average. So in general, the moving average predictor lags behind dramatic changes in the behavior of the process. And by the process, we mean the time series. So if there's a massive drop or a massive increase, it's not going to catch that right away. Because again, we're averaging. Oh, phone's going off. Of course, phone's going off as I'm trying to do a lecture. Great. Let's keep going anyways. I'm not going to answer that right now. You can call back later. Predictions for t is equal to 6 through 36 are one step ahead predictions because again we're just predicting one step into the future. So the mapred.wge command used in the exercise specifies up to 4 steps beyond the end of the data set. So if I did n.ahead is equal to 4, I'm predicting 4 steps into the future. But everything that we've done at this point is just one step into the future. So the prediction, and this is just a kind of a thing to note here, the prediction at 37 is the average of the last 5 data values. So that's 35 or 32 all the way up to 36. Those are the observations, the true observations that I have. But now what happens when I'm trying to predict past the point of the original data? So, well, past the point is, again, 37. That's one step into the future. But I'm using 5 data points that we actually have before that. What happens if I'm trying to predict time is equal to 38? Well, I don't technically have those data points or 5 data points that come before because it ends at 36, but I need 37. So now in order for me to do this calculation, I'm taking a predicted point and using that into my data. So I'm taking a point that I've already smoothed and I'm smoothing it out again. So what's going to happen when we notice, or when this is going to happen, is this is going to flatten out very, very quickly. Now, another thing to note, again, because I'm predicting and I have to use a predicted element in my calculation here, and it's just one predicted, this is called a 2-step ahead forecast. So that's simply it here. Where's my pen? So I have 4 original data points in there. I have 1 predicted point, so this is my 1 step ahead into the future. But now I'm doing an additional step ahead, so now I'm 2 steps ahead. Okay. But let's actually see this. Let's jump back to R for a second, and let's change this up. Let's go back to exercise 5, and instead of doing 1, let's do 10 into the future. If I do this, plot this up here, notice again what's happening is this line here. Everything just kind of flattens out because that's all we're doing. We're taking averages of averages. So all of those fluctuations that we removed in the moving average, we're removing even more of those fluctuations as we take an average of an average of an average and so on and so forth. Hopefully you're getting the point at that point. So that's why, again, it's kind of flattening out at this point in time. So if there was trend, there was seasonality, we're definitely not going to be able to capture it in this because it's just going to plateau. All right, so now we're going to move on to the next step up, which is exponential smoothing. So if we think about what's happening with the moving average, yes, we are trying to smooth things out. And we're going to do that same thing in exponential smoothing. We're going to try and smooth out those fluctuations, but how we do it is going to be different. So how we did it in terms of the moving average was I grabbed, in the last example, 5 data points and I took the average of those. Now, what I'm doing when I'm taking the average is I'm not specifying a particular weight at any one of those observations. So that means I'm treating those 5 observations exactly the same. So that means the one that came previous, the month before that, the month before that, the month before that, we're giving it all the same amount of equal importance in terms of this calculation. But does that actually make sense? Let's think about that for a second. The naive approach says, I'm going to use exactly the same thing that I did last time, because that worked. Here I'm saying, for the moving average, let's take the last 5 and treat them all as equally important. But maybe, here's the thing, the most recent one should have more emphasis. It should play a more important role when doing this forecasting. We should be using other things as well inside of there, but in terms of level of importance, we should give it a weight, saying, I want to make sure that this is being a centerpiece for us, and then everything else, it's going to add in there because things that happened in the past should play a certain role, but what happened most recently should be the most important to some weight. And that's basically what this first little bit is telling us here. Where's my mouse? Is that, again, we're just treating them all exactly the same. So it is more intuitive to believe that in many cases, more recent data should have more influence on future values than data in the more distant past, because it is more relative of the current state of reality. So we're not forgetting what's happened in the past, but we're not going to emphasize it as much. Again, that moving average, everything is treated, everything in the order, so those observations, k observations, everything is treated equally fine, or equally the same. All right, so the general idea here is we are going to build a weighted model with emphasis on the direct previous data value. And why we call it exponential smoothing is because the amount of influence on past observations becomes exponentially small the farther we get down that line. So if I'm trying to predict at time 100, I'm going to look at time 99. That's going to be the most important. And then everything else, we're still going to include it, but it's going to become less and less relevant. How less relevant? It's going to become exponentially small. So a little bit of the theory side of things here. So consider that each data value, x sub t, in a time series is comprised of a mean value at each point in time t and an independent error term with zero mean and constant variance. So we have an average for each one of our points. So at time t, it has a specific average, and it's just going to shift slightly from there based upon the error to get to the true value. So whatever the average is, shift the error. Basically, like if we're trying to do a line of best fit, the line of best fit gives us the average, and where the distance is between the true value, that is our error. That's just going to get us to that point in time. So it's the same idea. So now we're going to pick an alpha, or alpha is going to be between 0 and 1. Think of it as 0% all the way up to 100%. This is going to be the level of importance that we are placing on the most recent observation. So how do I calculate the average for time t plus 1? Well, what I'm going to do is I'm going to take, well, what was the average at time t? I'm going to scale that by something. That happens to be 1 minus alpha. Again, alpha is that level of importance that I'm putting on the most recent observation. So I'm saying my average of getting to t plus 1, I'm going to scale that data point that came previous to this by alpha. So what is the weight of importance? If that's 75%, that's 75%. My average is coming from that most recent data point. And then the average of the remaining data points of the time previous to that, that's going to be whatever is left. So if it's 75% going to that observation, it's 25% going to what's remaining. So this is a recursive construction on there. We can expand all of this stuff out and write it in the following way, where I can say that the average at time k is just going to be the sum from j is equal to 1 all the way up to k minus 2 of really this mess here. Now, I'm not going to go through this in that great of detail because, again, that's beyond the scope of what we're trying to do here, but just notice kind of the general idea of this. So when j is equal to 1, what do I have here? I have 1 minus 1 gives me a 0, so this 1 minus alpha is just going to be 1. So that first time when j is equal to 1, I just have alpha, and this is going to be k minus 1. So this is going to be that most recent observation. And then for each other observation, I am just changing that exponent, that 1 minus alpha. So whatever is remaining, if that's the 25%, because I put 75% up to begin with, well, I'm just shrinking that down by, again, raising that to a higher power. So if I had a number that's less than 1 and I keep raising it to a higher and higher power, it's going to become smaller and smaller exponentially, which is, again, this whole idea of this exponential decay in the amount of importance that we put on those previous observations. So the farther we get away down that line, that's exactly what's happening here. And then until all the way down to the very last observation. So I'm using all of the observations. So it's not like the moving average version of this, which I'm saying I'm taking the 5K observation. I'm taking all of the observations. But again, the level of importance that I'm putting on it becomes exponentially small the farther down that line I go. So how do we do this inside of R? We are now using the xsmooth function .wge. WG, if you're ever wondering, that is just there's three, this is all coming from a textbook, three authors, last names, one was with a W, one with a G, one with an E. This is probably the first time I've actually seen it in functions that people have actually put their last names in there, or the first initials of their last names. Hey, cool. You create the things, you can do whatever you want. I just think it's kind of funny. So what do we put in here? We put in X, which is our time series, alpha, that level of importance that we can specify, and how many steps ahead that we want to go into the future. Now, what kind of things to note? What are the values that we should normally choose? Well, alpha is normally chosen between 0.2 and 0.4. So we're not putting an exceptionally large amount on the time that came previous, but still enough such that the times that come afterwards, as we start building down, there is some level of importance on theirs, but again, it's going to decay exponentially. Same person calling. I get it. Relax. I will get to you. All right, so for exercise 6, we're going to use that same data set. So that's the WT crude 2020. And again, we're going to apply a one step ahead forecast using exponential smoothing. And I'm going to say our alpha is going to be 0.4. And we're going to do the same thing. We're going to calculate the errors. All right, so let's jump over to R to be able to do this. So this was all under exercise 6. So I'm going to store in the variable wtc36.exp. This is where I'm going to store all the smoother information. So I'm using the exp smooth.wge. WTC36 is the name of our time series, alpha being 0.4, and I'm doing one step ahead into the future. All right. What else do I want to do? And we wanted to be able to calculate the error on this. So the error last time was 3,261. Well, actually, let's print this out to the screen first. WTC36.exp. There we go. So my predicted value this time around is 42.98189. There we go. So what was the predicted value last time? The predicted value is 42.02270. Okay, so it's a little bit bigger. Again, taking that most recent information and it's becoming the dominant part of this. So we want to now calculate the error. All right, so calculating the error, I'll get rid of this line. I don't have this in my original one. There we go. I'm just taking the original minus the smooth values here. Notice this time, when we're doing this, what is the error the first time around? The error is 0. Why? Because it is just the predicted value is the original value. There's no information to take previous to that, so that is all it is. It's 100% of that. But as we go down that line, there is going to be a difference. That's exactly what we see. So at position 2, it's negative 1.46, blah, blah, blah. Position 3, negative 0.132 and change. So there is a difference. But at that very first point, it's going to be 0. Now, I don't have to do the remove all the NAs because there's no NAs this time around. Excuse me. So I just want to sum all these up, but I want to sum the squares of all of this. So summing the squares, I get 2,314.963. So again, the last time we were 3,000 and change, now we're 2,000 and change. The smaller the number that we have, the better the approximation or the better forecasting that we are in fact doing based upon the data that we do in fact know. So this would be better than the centered moving average. And we did this at a 0.4, so we can try different ones. And I leave that as kind of an exercise for you folks, is try different alphas. Because a different alpha is going to give you a different predicted value. And how is that going to change in the model overall? Are we getting worse? Are we getting better? So try a different range of them. Start at, say, 0.1, go to 0.2, 0.3, 0.4, all the way up to say, well, I wouldn't go to 1, because if we hit 1, what are we doing at 1? Well, 1 is just naive. That's it. So if we have a 1, we have a naive model, and that's complete. It's not useless to us, but again, we should change models if that's what we're using. All right. So a couple of things to note here. For t within the time frame of the data, ut plus 1 is the estimate of the mean of ut plus 1. There should be a squiggle there. That should be the estimate of the mean, given the data up to and including time t. So when t is equal to n, so when we're talking about the data that we actually have, the end of the data set, then tn plus 1 can be calculated using the data up to and including time n. That is, the prediction equation gives an estimate of n plus 1. Now, because there is no assumed trend or seasonality in the data, exponential smoothing predictions beyond the end of the data is based on the assumption that, based on what we know at time t is equal to n, that is our best estimate for what comes next. So what do I mean by that? Let's go back and let's see this inside of R. We did one step ahead. This time around, let's do 10 steps ahead. And I do this. And notice it plots here automatically for us, and this is our predicted line here. Notice at that prediction line, I don't have any squiggles as I did the time before. It's not smoothing anything out. At the end of it, it's just that very last observation. So basically, after that next point in time, so after we predicted one step ahead into the future, which we could, everything that comes after that point in time is just based upon a naive way of doing things because, again, that's the best that we know. No trend, no seasonality, nothing, no fluctuations that are happening in there. It just instantly smooths right out. All right, so last but not least, Holt-Winters forecasting. So this is an exponential smoother as well, except it's going to take into account trend and seasonality. Now, I don't want to get too much into the equation here because really, even in a fourth year class, and you've had to have done a lot of stats, we don't go too great of detail of all of this. But basically, we have three main components in here. So we have a U sub t, so we still have the average of what came before that, but we also have a V sub t and an S sub t. So this is taking into account our trend and seasonality. So think of U sub t as your best guess of the underlying baseline after removing trend and seasonality. Then you have the trend, which is just going to be the average change per period. So are you growing positive trend or are you shrinking negative? And then seasonal, the average deviation in each month or quarter compared to the baseline. So this is kind of like the holiday boost that we can kind of think about. And that's really what's kind of happening in here. So we're trying to remove information which we already know and kind of isolate those kind of key components here. So what is our baseline, our best guess? That's our average, our U sub t. Then we have that trend, which is our V sub t, and then we have our seasonality, which is our S sub t. Now notice that there is an alpha, beta, and gamma in here as well. So we have to do choices of these. Well, actually, we don't have to do choices because if we use the function call already, it will estimate what the best alpha, beta, and gamma are going to be. But if we wanted, we can include or we can specify which ones that we want. Now, there is going to be times where, we might have a model that has trend but does not have seasonality. For seasonality, I need to see repetitions happen within a year's period of time. If I have just yearly data, I'm not going to see a seasonal aspect of things. So I can't have a seasonal component to it. It may have a trend, but not a seasonal component to it. So if I want to use this, I can set the gamma equal to false or null or something along those lines. I can't remember off the top of my head. I'll have to think about that one for a second. But I can basically shut off that parameter which says I'm not going to use seasonality. I still want to use trend here. Or I want to take off trend and I just want to use seasonality. So we can isolate those parameters and shut them off, which is perfectly reasonable. And I think I even asked that in one of the assignment questions there. But for choosing these, again, it's that level of importance. So it has to be between 0 and 1 or 0% and 100%. There we go from there. Now, putting this all together kind of gives us these annoying sort of equations here, where we're simply just saying that x sub t, or the prediction of x sub t, is equal to the sum of these three things. So it has the average, it has a trend, and it has a seasonal component to it. And if we're predicting into the future, that's all this is telling us here. So after time n, we're doing n plus L, so predicting into the future. This is going to use a U sub n, MV sub n, and the seasonal component, again, we're just making sure that we're choosing the right month, quarter, whatever we need for that seasonal component. This is a little bit more complicated in terms of the formula. I wanted to keep it as completeness as possible. You don't have to memorize this. If you want to go through it, there's office hours. I'd be happy to spend an hour with you kind of going through the ins and outs of all of this, but it's not something that you need to know for this, just the understanding of we're putting all of those components together. So there's the additive part of this if we have an additive model. There's a multiplicative part of this if we have a multiplicative model. Again, that's kind of where the variance and the squiggles come into play. We saw that already. So let's use a data set that we already know has trend and seasonality to it. So that's the air passengers data set. So I'm going to use a Holt-Winters model. I'm going to build that model, and then I'm going to use the predict function to be able to predict into the future. So we're just building the model and then based upon that predicting from there. So think of this as the same thing as building a linear model and using the predict function to predict into the future. We're doing exactly the same thing. We're building a model or a Holt-Winters model and using predict to predict into the future. Oops. All right, so let's jump over here for a second. And by jump over here, I mean I looked at the other screen, but I got to change up here. There we go. All right, so let's do the additive model. Oh joy, it's done it again. You get a new computer and things still crash. Where was I before here? Did this. What exercise? Sorry about this, folks. There we go. Now we're back up and running. Hopefully I can make it through the rest of this lecture without this crashing on me. There's not much left to go, but here we go. All right. So we're using the additive, so I have to take the log of the air passengers data, because remember the air passengers data does have those squiggles at the very beginning, which is small and then gets larger. So the variance is increasing over that time. So if I take the log of this, it's going to change from a multiplicative model to an additive model. So I'm storing that in ap.log. Now I'm going to use the Holt-Winters function. The first parameter is going to be my time series, so the ap.log, and I'm setting this seasonal to additive. So just letting it know that I'm dealing with an additive model. Now I haven't specified anything for my parameters, so it's going to find the best alpha, beta, and gamma. So if I do that, and I'm storing that in ap.hw for Holt-Winters.a for additive. It's a list of 9 things. So if I just open this up here, there's a few things in here. So notice my alpha has a 0.327, my beta is 0.00574, and my gamma is 0.821. So that's a high level of importance going to seasonality, not so high of an importance going to the most recent in terms of trend. But definitely there's a lot of importance going into what just happened to help us predict in terms of seasonality. Now, if I plot this, hopefully you'll be able to see this if you're following along playing at home, the home game, yay. You're going to see a red line and you're going to see a black line. So the red line is our predicted, the black line is our true value. What do we see from this? We see things matching up. So the ups and downs, it's responsive in the same way, or not in the same way, I was going to say the same way as the centered, or not the centered, the predictive smoother. Predictive average smoother. There we go. Because in that one, when we saw massive drops or massive increases, it took a little while for us to get to that point in time because we were taking the average. Here we're getting something that is very responsive. There is fluctuations. It is slightly different than, it's not hitting things perfectly as it was in there. But again, these are estimates based upon the overall trend in seasonality. And we can see based upon this, it looks like it's fitting fairly well. Now I want to predict into the future. So using that predict function, I'm going to put in my model, I'm going to put n.ahead 36. So I don't have to specify a data frame or anything else along those lines as we did beforehand. I'm just saying I'm going to go 36 steps into the future. And if I do that, now I can plot the two side by side. And what you should see on your screen is up to a point in time, which is going to be right around here. We have a solid line that ends, and then we have dashed lines in here, and this indicates our predicted values. So notice in terms of predicted values, the trend of the data is still going upwards. These are still going upwards. The up and down seasonal effect is still actually modeled in exactly the same sort of way. So in terms of being able to capture trend and seasonality, it looks like it's doing a fairly half-decent job at that. Do I have... Yeah. I'm going to talk about accuracy in just a second here, so I'm going to skip over that part. Let's go to my next slide. So my next slide, I'm not going to go again into too much detail. This is just the multiplicative version of this, so there's still going to be a baseline trend part to this. There is going to be, sorry, a baseline average of this. There's going to be a trend component. There's going to be a seasonality component. How we remove things, we're dividing instead of subtracting. And same idea when we put everything together, it's going to be a product of things instead of just a straight addition of things. Exercise 8, I will leave that for you folks to play around with. All it is doing exactly the same thing. I do have the code already in the slides, so you're welcome to kind of go through that. But the idea of this is still exactly the same. So here, in this case, we're not going to change it to the log air passengers data. What we're going to do is use the original data because the original is multiplicative, and we're going to see, does the increase in the squiggles still take into effect when we predict into the future? The answer to that is yes, it will, but double check that. Make sure I'm not just fibbing to you. All right, so the last little bit here is assessing the accuracy of the forecast, and this is the things that we've already been doing. But we're going to go into a little bit more detail here. So how do we assess the data? Well, if we predict into the future and we don't have what those future values or the true values are going to be, we don't know how good the accuracy is going to be of our model. But one of the things that we can do is we can cheat a little bit. Let's say I had multiple years of data. I'm going to break that data up into two different categories. Think of it as a testing and training. We hear this a lot in the data science world of things. I'm going to train my model on a specific set or a specific time series. I'm then going to test it on data that it hasn't seen yet, but data that we actually know exists, so I can predict into the future. So if I had like 12 years worth of data, I can say, let's take the first 9 years. I'm going to build my model on the first 9 years. I'm going to use this model to predict the next 3 years into the future. I have the next 3 years of actual data, so I can compare how good my model is to those 3 years that I do in fact know. And that's exactly what we're going to be doing here. So what is the metric that we are going to be using? Well, what we've done up to this point in time is we've just taken the sum of squares. But what we actually should be doing is we should be taking the mean sum of squares. What is the average? Or realistically, the RMSE, so the root mean sum of squares. Because again, we're taking each one of the observations, the distance away from the true value, we're squaring that, then taking the average of that. Really, it's like the variance, we want to break it down to the standard deviation where we're putting it back into its actual units, not squared units, so we take the square root of that, or the root MSE. So the RMSE is the units of the problem, is the same units of the problem that we are in fact dealing with. Otherwise, the MSE is going to be the squared of the units. It is the sort of average amount by which the forecast differs from the true value. There we go. So the very last thing that we're going to do is we're going to do exactly that. We're going to take the air passengers data, which is 12 years worth of data. We're going to take the first 9 years. That's what we're going to be training our model on, and then we're going to be testing it on the remaining 3 years. So I'm going to use the model we just built on the original 9 to predict 3 years into the future. We have the true values for those 3 years into the future. We're going to compare the two and see how good the model actually is. All right, so let's do this here. Got to go back to my other screen, but as soon as I find my mouse, there's my mouse. Change up my screen. Here we go. So exercise 8, I'll leave this for you folks to play around with. Assessing the quality of this. So the first thing that I want to do is I want to take the first 9 years. So I'm going to use a start and end. I don't really need start, but I can just use end if I wanted to, but might as well use both of them here. So we're starting at 1949 month number 1, going all the way up to 1957 month number 12. I'm storing that in AP9. That's for my 9 years. Now I'm going to call AP9.HW. We're going to use the Holt Winters model here. So I'm taking the AP9, which again, it's not the log air passengers data. It is just the original air passengers data. So it's multiplicative. So I'm putting the seasonal to multiplicative. Now using the predict function, I built my model. Again, that model is stored in AP9.HW. So I'm going to go 36 months into the future, or 3 years. And now I want to plot alongside of my original data here. So what you're going to see in the last 3 years, I have solid black lines, I have dotted black lines. The dotted black lines are our predictions, the true black, or the solid black lines are our true values. So notice we have some bigger spikes here happening, so the variance increases a little bit more than what our model predicts. Well, that just might be because at that point in time in the model, it naturally was going to increase much, much more. The model didn't capture that because it only used the 9 years previous. So that remaining 3 years, there might have been a bigger increase than what we would have expected to see. But again, the same trend, that same increase in squiggles still happens as we would expect it to. So now I want to compare this to the actual data. So how far away are these dotted lines to the solid lines? So I'm going to create a time series called actual, which I'm taking the air passengers data and I'm just starting it and getting the last 3 years. So my actual data is here. So starting in 1958 all the way up to 1960, I have 36 months worth of true data. I'm going to call pred the predicted value. So I'm just taking the ap9.pred, putting it into there. And if I want to show these, again, rounding it to 0 decimal places. So what I have here is my actual values. Here are my predicted values. So my error is going to be the difference between the two. And if I wanted to round and put out the error in there, again, number of passengers that we differ by. So January is 4, February is 18, 36, 38, negative 16 for June, so on and so forth. So if I wanted to calculate the mean squared error, all I'm going to do is I'm going to take that error, I'm going to square it, and I'm taking the average of that. So this gives me my MSE. But I want the RMSE because I want it back in its original units. And if I print this to the screen, I get 44.83713. So rounding it to 3 decimal places, what does this mean? That means 44.837 passengers on average differ from the forecasted to the original. That might be good enough for us. We may want to adjust things, adjust the alpha, beta, and gamma to potentially get us better predictions. But again, we have a baseline now for being able to compare these different models. So that's it. That's all in terms of the forecasting. We'll get into the very last lesson, so we should just have one more lecture overall, and that will sum up everything that we need to know for now. So we'll see you back here shortly. Until then.